Okay, here we go with example number 1. It says use the approach in Gauss's problem to find the following sums of arithmetic sequences. Do not use formulas. Okay, so we need to know some stuff before we can get started working on these problems. First of all, let's reread the directions again because directions are incredibly important. It says use the approach in Gauss's problem to find the following sums of arithmetic sequences. Okay, so first of all, you have to know what an arithmetic sequence is before you can even begin this problem. And you should be familiar with the term. You saw it in college algebra or pre-calculus, or algebra 2 if you were in high school or something like that. But you may not remember what they are, so let's go back over that and make sure that you understand. An arithmetic sequence is a sequence of numbers, just a listing of numbers where they go up by the same amount each time. So for instance, in this very first example here, problem part A, you go from 1 to 2 to 3 to 4. So each one of these is going up by 1 each time. You're adding 1 to get to the next term. When you add the same amount in order to get from one term to the next, to the next, to the next, that's what's called an arithmetic sequence because you are adding to get to the next term. Um, so we need to know that first of all. Now, second of all, we need to know what Gauss's problem is so that we can follow that and understand the logic behind that. So let me bring up a blank page and let's talk about what that means. Okay, what there was a guy a long time ago named Gauss, Carl Friedrich Gauss, who evidently was a little bit of a you know normal child and went to a school where at the time they didn't have like paper and pencils and things like that. They used little chalkboards and that they had at their desks, and they would write their answers on it. And supposedly, the way the story goes, evidently the class was particularly rowdy one day, and so their headmaster, their teacher, had told them to sit down and count, find the sum or add up all of the numbers from 1 to 100. And supposedly Gauss figured out how to do it very quickly and came up with the answer. And the teacher thought it would take them, quite a while to add all of those numbers. But what happened was Gauss figured out a pattern. So what he did was he said, well, let's just look at this written out. If we add 1 plus 2 plus 3 plus 4 plus dot 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 all the way up to 100. So we'll say, like, 97, 98, 99, 100. Well, that's 100 things that we need to add up. But look what happens if we go backwards. 100 plus 99 plus 98 plus 97 plus dot 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 all the way down to 4, 3, 2, 1. If you were to add up each one of these numbers in line, 1 and 100 is 101, 2 and 99, that's 101, 3 and 98 is 101, 4 and 97 is 101. Each one of these sums adds up to be the exact same thing. So what he did was he said, look at that, I have 100, 101 sums. So if I take 101 and I add it together 100 times, that's the same thing as saying 100 times 101. And so he went to his calculator and he figured out what that was. And let me grab mine really quick because I didn't have that out. So 100 times 101 is 10,100. Okay, but he said, I'm not done yet because that's too much. Because that was like saying we've got twice as many of these 101 sums as we would have if we had just added 100 and then the 1 and the 2 and the 99 and the 3 and the 98 and the 4 and the 97 and so on and so forth. So we've actually doubled the number of 101 sums that we had originally. So what I need to do now is I need to divide this number by 2 because I only need half of these. So when we divide that by 2, we get 5,050. So that is the sum of all of the numbers from 1 to 100. So, and he figured that out when he was fairly young. So, I mean, not a teenager by any means. He was a preteen. So that's very interesting. But that is where, if you're looking for a pattern, and that's what he was doing, he saw that pattern and said, hey, I think I can use this to my advantage. So that's what I want you guys to do also. All right, let's go back then, if I can get my thing to pull up here, and let's see what we need to do. This says use the approach in Gauss's problem to find the following sums of arithmetic sequences. Do not use formulas. They say don't use formulas because there actually is a formula that you can use to sum the numbers from such and such to such and such. But we're going to, instead of that, we're going to be using our problem solving skills to be able to figure it out. So the first one is 1 plus 2 plus 3 plus 4 plus on and on and on up to 99. So this one is very, very similar to the one that Gauss did. So if we were to add if I were to rewrite those backwards and say 99, 98, 97, 96, all the way down to 1, each one of those sums would be 100 this time, wouldn't they? I'm trying to write tiny. I know it's kind of hard. So I have how many of those 100 sums? I actually have 99 of them because there are 99 numbers in this sequence. So if I were to take 99 times 100 and figure out what that is, that would be 9,900. Simple enough, right? Now then, that is double, though, what we actually have, because we actually have half that many pairs. We doubled it in order to figure out what that sum would be. So I would actually need to divide by 2, which this is not good notation. I apologize for that. And so 9,900 divided by 2 would be 4,950. Okay, now let's try one that's maybe just a little bit more challenging. In this one, we have 1 plus 3 plus 5 plus 7 plus on and on and on, all the way up to 101. So first of all, let's try to figure out what's going on in this problem. This is an arithmetic sequence because we're going up by the same amount each time. We're actually adding 2 to get from one number to the next, and then adding 2 to get to the next one, and then adding 2 to get to the next one, and so on and so forth. So this is an arithmetic problem. All right, so what we're going to do here is we're going to rewrite this, and I'm going to write it out so we have a little bit more room. So that would be 1 plus 3 plus 5 plus 7 plus on and on and on. And I'm going to write out a few more terms just before the 1001. So I'm going to start at 995, 997, 999, and then 1001. So we're going up by twos each time until we hit 1001. Okay, now I'm going to rewrite it right here below, and this time I'm going to start at 1001 and go down to 1. So 1001 plus 999 plus 997 plus 995 plus dot 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 plus 7 plus 5 plus 3 plus 1. So now I'm going to have twice as many pairs as I should have, but that's okay. At the end, we can just divide it by 2 to figure out how what our true sum should be. But by writing it this way, we can see that each one of these sums, if I add up this in column format, 1 and 1001 is 1002, 3 and 999 is 1002, 5 and 997 is 1002, and it goes so on and so forth all the way up. So dot dot dot, big dot 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 in the middle. So we've got all of these pairs that create 1002 as their sum or their addition. Now what we need to figure out though is how many of those pairs do we have? And because they're not going up by 1, they're actually going up by 2s. We can't just say, well, like we did in the first problem, there's 99 numbers, or like we did in Gauss's problem, there were 100 numbers. In this one, we need to figure out kind of the pattern of what's going on. So I want to kind of look at this just for a minute and show you a good way of being able to figure that out. Let me write the term, just the first few terms down here. Let's see, our first few terms are 1, 3, 5, and 7. Now, I'm going to now over here write down the number of the term, meaning that 1 is our first term, 3 is our second term, 5 is our third term, 7 is our fourth term. Okay, so now let's try and see if we can figure out a pattern, because the number of the term we usually call n. I don't know if you remember that from college algebra, but we call that n. So we got to try and figure out a pattern that uses n that will get us back to this number. So do you notice anything cool about starting at 1 and getting 1? Well, it is itself. What about starting with 2 and ending up with 3? Well, we could add 1, but that doesn't work for the next one, because if I add 1 to 3, I don't get 5, I'd get 4. But do you see any similarity or pattern here at all? I know that if I take 4 times 2, I get 8. And this number is 1 less than that. If I take 3 times 2, I get 6. And this number is 1 less than that. If I take 2 times 2, then that's 4. And this is 1 number less than that. If I take 2 times 1, that's 2. And this is 1 less than that. So if I double any one of these and then subtract 1 from it, I end up with whatever that term was. So that's our pattern. So each term is double the number of the term and then subtract 1. So if we know that 1001 is, following the pattern, 2 times n minus 1, we can solve for n, and that will tell us what the number of the term is, or how many terms there are. So if I add 1 to both sides, I get 102 equals 2n, and then if I divide both sides by 2, I get n equals, 501? So 1001 is the 501st, or 501th, that's not very right, 501st term. So that's telling us that we have 501 of those pairs of 1002. So 501 pairs of 1002. If we multiply that together, we get 500, 2002. But remember, that's twice as many as we should have. So I need to divide that by 2 to get, and I'm running out of room here, 251,001. So if I sum up all the numbers between 1 and 1001, but I'm going up by 2 each time, that would actually equal 2,501, or 251,001. Sorry, I said that incorrectly. I'm kind of losing my mind here as I go. Okay, let's try one more because that might have been a little confusing. So I want to try one more to see if we've got the pattern going down here. So this one is doing 3 plus 6 plus 9 plus 12 plus dot 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 all the way up to 300. So I'm going to do the same thing again. I'm going to start off by rewriting 3 plus 6 plus 9 plus 12 plus dot 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 plus, now I'm going to write a few more terms here so that I can make sure and see. So if I would start it off at 300, each one of these is going up by 3. So to go down, I'd need to go down by 3. So that would be, what, 297, 294, and then 291, and we'll just stop there because I didn't leave enough space. Now if I rewrite that so that we can see that those sums are all going to be the same, I would have to start off with 300, go to 297, 294, and 291, plus dot dot dot, all the way down to 12, 9, 6, 3. So look at what's happening here. Each one of these sums happens to turn out to be 303. Notice that? That's kind of cool. So we have all of these sums of 303, but we don't know how many we have. So we have to figure that out too. So just like we did before, let's look at the first few terms. Our first few terms were 3, 6, 9, and 12. Now let's look at the number of the term, or in other words, n. Our first term was 3, our second term was 6, our third term was 9, and our fourth term was 12. Do you see a pattern between n and the actual term itself? Do you notice that if I multiply n by 3, I get the term itself? The first term, or 1, times 3 is 3. Second term, or 2, times 3 is 6. Third term, or 3, times 3 is 9. And fourth term, or 4, times 3 is 12. So each term is 3n. So if we know that 300 has to follow that pattern, if 300 is 3n, we can solve for n, and that will tell us how many terms we have. So that means that n equals 100. So we have 100 pairs of 303s. So 100 pairs of 303s, that would end up giving us 30,300. Now that's twice as many as we should actually have, so if we divide that by 2 we get 15,150. So that would be our sum.